Hello, and welcome back to the Mechanochemistry discussions. This seminar series is hosted by the NSF-funded Center for Mechanical Control of Chemistry, or the CMCC. I'm Ashley Martini. As always, the goal of our seminar series is to bring the mechanochemistry community together. The seminar is streamed live on the third Thursday of every month at 11 a.m. Eastern U.S. time and are available to watch anytime on the YouTube channel. We've had a great group of speakers so far as part of the seminar series, and they are again all available to watch on the YouTube channel. We also have a great group of speakers lined up for the upcoming months, and we hope that you will join us for all of them. Before we get started, a few quick thanks. Dr. James Batiste, the Center Director, Jennifer Belsick, the Center's Administrative Coordinator, and Katie Floyd, a CMCC student, without whom the seminar series would definitely not be happening. Also, thank you for joining us. Please do subscribe, follow us on YouTube, as well as on Twitter. Finally, reminder that the seminar is being recorded. If you have questions, you can email them to us at cmccdiscussions@gmail.com, or you can post them in the YouTube channel. Either way, they will be propagated to the speaker at the end of the seminar to be answered at that time. Last but not least, it's my great pleasure to introduce today's speaker, Dr. Claire Mayer. Dr. Mayer is a research engineer at the French National Institute for Agriculture, Food, and Environment. She began her career in 2005 as a process engineer and spent some time in industry before completing her PhD in chemical engineering in 2012. Subsequently, she joined the Joint Research Unit IATE in Montpellier. From 2012 to 2020, she managed a research facility dedicated to plant materials processing. From 2020 to July 2023, she worked as a visiting researcher at Scion Research Institute, thanks to a Marie Curie grant that she obtained in 2020. She has coordinated numerous research projects, primarily focusing on the design of functional and high-performance powders from lignocellulosic biomass through mechanical deconstruction for applications in chemistry, energy, and materials. It's our pleasure today to host Dr. Claire Mayer.
So, hello. Today I will speak about the fundamental of lignocellulosic biomass mechanical deconstruction and application to mechanochemistry. So today my speak will be focused on 3 points. The first, I will introduce my background and the facilities that we have at INRAE for the mechanical deconstruction. Then I will speak about mechanical deconstruction from a physical standpoint. And in the third point, we will see how we can apply that to mechanochemistry. So I'm a research engineer working at INRAE. So INRAE is the French National Research Institute for Food, Agriculture, and Environment. So my lab is located in Montpellier, so in the south of the France. And during 8 years, I manage facilities from INRAE, which is a technological research platform for the mechanical deconstruction. And I was also involved in the FIPRODIV team, which is a research team working about the physical of process for divided solid. During 3 years, I went to Scion in New Zealand, which is a Crown Research Institute, in the farm work of a Marie Curie grant, and I was working about the use of plant powder for additive manufacturing. So on the slide, you have a picture about me and my colleague working on additive manufacturing and the research team in which I was involved when I was there. In the framework of this collaboration, we start to work to mechanochemistry and try to combine, in fact, lignocellulosic biomass with mechanochemistry to functionalize some materials. In the framework of this collaboration, we create an international associated lab, the LEA Biomata, and the work I will present at the end of my presentation have been realized in this framework. So first, I just want to give you an introduction about the Planet facilities, which is our research facilities for mechanical deconstruction of plant materials. So the facility is on an area of 800 meters square, so of technological halls. We also have a research, a technical team working on the platform with 6 to 7 full-time equivalent people. The platform gathers more than 100 pilot square equipment, and for us, it's a choice case of the research activities that we have in the lab. So for different type of application, food, feed, packaging materials. So on our facility, we have different, area. One is more dedicated about cereal fractionation, because at the origin, the lab was a lab for cereal fractionation. And as we are working on cereal fractionation, we decide to work on cereal byproducts. So we start to work on straw and other lignocellulosic materials. And so now we have some facility dedicated to the transformation of this, of plant materials. And also we have some facilities for plant powder property, which is quite important just to manage the property of the end product. So here we have some example about the capabilities that we have. So different type of ball mill. I will speak a little more about this ball mill later, and also some process for the separation of powder after the milling. We also have some facility for powder characterization. So for example, here we have a particle size analyzer, particle shape, microscopy, but also we are able to measure the flowability of the particles, the specific surface area, and other properties. So in the research team FIPRODIV, we study the physical process involving plant-divided solid with the aim to understand, modelize and optimize, in fact, the property of the materials. So we are working at different scale. The scale of the interaction, it can be molecular interaction a bit inside the particles, but also interaction between two particles. Rheology, which is more at the scale of the powder bed, and processing inside, so inside the process. We are using both experimental and numerical tools, as you can see on the slide there. So my research activity focus on the mechanical deconstruction of plant materials. So on the left, you have a word cloud about some main keywords of my research articles. So you can see that the focus are on combination, powder, and lignocellulosic materials. We also have a small picture, which is from a French website, IFP Énergie Nouvelle, which give a good idea about the importance of understanding how the lignocellulosic biomass is deconstructed just to replace fossil raw materials. So in fact, when we are speaking about lignocellulosic biomass, we are speaking about one materials, but it's much more complex because lignocellulosic biomass have a complex structure. So lignocellulosic biomass comes from the plant cell wall, as you can see in the picture here. And it's not one molecule, but in fact, it's made of three main components. The cellulose, most of the time it's cellulose under fibrous form, hemicellulose, and lignin. But when we speak about lignin, there is not only one lignin, but there is different type of lignin, and all of that are together and constitute the lignocellulosic matrix. In addition, the proportion of each component vary according to species and also to some specimen that we can have in the same species. What we believe that in fact lignocellulosic materials can be a wonderful reservoir of functionalities. These functionalities arise about a combination of physical and chemical property, and just to activate them, we used in fact a mechanical deconstruction. So when we are speaking about property of the powder, in fact, we are speaking about different type of property. Some property is what we say intrinsic properties. So it means that it's a property of one or several particles, the size, the shape, the specific surface, the surface composition, the bulk composition. And we also have some bulk properties. So this property arise for a combination of several interesting properties, and also with environmental factors like humidity, for example. Both properties drive, in fact, the behavior of the material inside the process, for example, inside a grinding process, and so drive also the functionality and the quality of the end product. So these powders are obtained by grinding, and so it will be the first focus of my presentation today. So when we speak about mechanical deconstruction, we can speak about milling, but also about separation, because sometimes we use separation just to obtain some remove some particles that, for example, will not have the targeted properties. So today I will just only focus on milling, but we also have some work that we conduct about the separation of powder. So milling can be realized in plenty of type of equipment. So it's very difficult to know in general to range, in fact, the different equipment. So in this slide, I try to do a mapping about the different milling technology. So it's commercial technology, and I rank them according to the size that we can target, the target particle size, and also the energy consumption, because in general, milling is quite huge, consume quite a huge amount of energy. So we can see that as the particle size decrease, for example, if you want to reach very small particles, which can be very useful in many applications, we will consume more energy. But there is another aspect that we can take into account is the power of the milling device. For example, some milling device like centrifugal mill, impact mill, or pin mill, we consume a huge amount of energy in a very short time. So we need a huge power. And for some other equipment, like, for example, ball mill, which is very interesting for mechanosynthesis, we can have some milling equipment that will consume a huge amount of energy, but on a longer time in comparison to other milling device. So this can be interesting for an energetics point of view, and if we want to have a sustainable process, because, for example, we can imagine that ball mill can be the energy for the ball mill come from, for example, a solar panel or other type of energy. So this classification will not help us a lot to understand what's happened inside a mill. So from a mechanical point of view, in fact, we can distinguish 4 different mechanical stress. So the 2 first one, compression and impact, will act in the bulk of the particles, and it's quite a similar force, if I can say, but in the first one, the compression, the force is applied for a longer time than in impact. Impact arises in a very short time. So the property of the particles that will result about the fractures path generated by the force will differ according to the mechanical stress. The 2 other one, shear and attrition, are also quite similar in the way that the energy transmitted to the materials. For example, as you can see here, it's transmit for shear in a transversal way, if I can say, but in force shear, it's transmit in the bulk of the particles, and attrition is more a surface mechanism. In practice, if we have a milling device, all the mechanical stress are applied at the same time and can lead with different type of particles. It's quite difficult to quantify the balance of each mechanical stress, but it's very useful if you want to play on this mechanical stress to drive the particles property. So for that, we work on a small milling device. So you probably know this device if we are doing mechanochemistry. So this example is a vibratory ball mill, for example. This one is just a milling device used, is a wrench milling device. So in this device, we have a ball. And so we have the ball is put in motion by a arm here. And so we have a vibration motion. So in this device, we can work with 1 ball, several balls, or plenty of beads. And what we try to do, we try to analyze which type of mechanical stress we have and how we can play on that. So we did discrete elements modeling of the milling here. And in one case, we work with 1 ball, and in other case, with plenty of beads. So here we have a little movie. So you can see the motion of the ball for 1 ball, and here the motion of plenty of ball. And so what we record, in fact, the impact, and we measure, in fact, numerically measure, in fact, the power that is lost by impact or by shear. And so in the first case, with 1 ball, the impact lost by the energy lost by impact is more important than by shear. And so we think that in this case, we assume that impact is the main mechanical stress. And in its other case, is the shear is more important than impact. And so we assume that in this case, we are more in a configuration where attrition is the main important stress. So this is for small milling device, but we work also in more bigger equipment, and we try to do the same work. So in this case, it was not possible just to quantify with numerical modeling because it was much more complex. So we conduct dimensional analysis of the milling device. And so we work with 3 different equipment. The first one is a rotary ball mill. The second one is a stirred ball mill. It's a prototype that we developed in the lab. And in the last one is a vibratory ball mill. So it's also a commercial device. We decide to relate, in fact, the impact to the kinematic energy of the ball and the attrition, which is like, it's related to friction, to the ratio between the surface of the ball and the surface of the powder. And based on this dimensional analysis, we can rank, in fact, the different equipment. And so this drive our analysis of the results that we obtain. So the first aim of mechanical equipment, a grinder, is to reduce the particle size. So we just try to see how these different milling technology influence the particle size distribution. Here we have an example about what we obtained for the milling of hard bran. And interestingly, we can see that the particle size distribution have different shape according to the milling device that we used. What is very interesting of this graph, we can see that in fact the population, we have different type of population, which seems to be approximatively for the same particle size, but the proportion of each population depend of the milling technology. So by playing on the milling technology, we can enhance one proportion of particle size or one other. Milling also influence other factors, like for example, the shape. And here is an example about what we did for the milling of flax fiber. On the left of the slide, you have the particle shapes that we obtain with a centrifugal mill. And so we can see, interestingly, that the particles conserve their aspect ratio. So it can be very interesting, for example, for a biocomposite application where we want to use this type of material as reinforcement. And on the right, you can see that with attrition, so the vibratory ball mill, we obtained very small particles, in fact, and so we break totally the fibrous structure of the material. We will discuss a little later this point. But the kinetics of the milling reduction can be quite long, as you can see here. So it's also for flax fiber. So here we can see the different D10, D50, so median particle size, and D90 for the flax. We can see that in the first milling time, the particle size reduced quite quickly, but after that, it's very long time just to obtain very small particles at the end. But we have modification on other property, like chemical property, and it will be the next point of my topic. So if we measure, for example, the elongation of finely ground particles for particles with a median size higher than 20 microns, we can see that, for example, for pine bark, which is a breathable materials, in fact, the milling device have no influence on the elongation, which is like an aspect ratio of the particle. But if we are looking about straw, we can see that with attrition, we can keep the aspect ratio, the elongation, even if the particle size reduced. And with impact, we have something like where with a more regular shape at the end of the milling. So this can be very interesting also to play on the property of the particles. So there is several models which have been proposed just to relate the energy consumption and the particle size reduction. So the most interesting model in our case for fine milling is Rettinger model. In this model relates, in fact, the milling energy to the specific surface area obtained. So if we apply that for the milling of materials, so this is an example on sand, on sound, we can see that for different, whatever, in fact, the condition of milling, we have the same curve, and all the curve fit very well the Retinger model at the starting point of the milling. But we see that for milling time, not for milling time, but for specific surface area around 1,400, the Retinger law is not working anymore. And so this is due, so we can relate that to the presence of very small particles, which generate agglomeration, as we can see here. And what is very interesting in this work that we can relate, in fact, the shift between the Retinger model and the real curve. We can relate that to the proportion of particles that have a size lower than 0.5 microns. So it means that for this size, we have some interaction, interparticular force, which become preponderant on the weight. And why they become preponderant? Because grinder also affect the reactivity and the chemical property of the materials. So we know that fragmentation reduces the particle size and increase the specific area, so increase the reactivity of the powder. But now we also know that ball milling decreases the cellulose crystallinity. So if we are looking, for example, about the result we obtain here for the grinding of wheat straw, we can see that for the same particle size, we can keep the cellular crystallinity with centrifugal mill and jet mill. But when we are using ball mill for a long ball milling time, the cellulose crystallinity reduces a huge. This is another example about how grinder affects the reactivity for cork. So cork has a honeycomb structure, as illustrated here. And with what is very interesting is that, in fact, the composition of the cell wall are different if we are inside the cell or outside the cell. Inside the cell, it's just some hair, so it's like a tennis ball, in fact. And outside of the cell, we have a mid-lamella with lignin, hemicellulose, and pectin. And inside, we have some suberin. If we are looking about the result we obtain when we are milling cork with different technology at different scale, we can see that if we have big particles around 500 microns, we have group of cell. If we are decreasing the size, we can have some isolated cell. And for very small cells, we have some cell wall fragment. And so by opening the cell, we can play on the composition, the surface composition of the particles. So we did some work when we have worked with some an impact mill here, and we have worked with a shear mill where we have more shear and here more impact. And what we observed that for cork, in the case of impact, the fracture paths propagate between the cell here. So it's mean that we didn't destroy the cell. When we are using shear, the fracture paths propagate into the cell. And so we can open the cell and make accessible the suberin part of the material. So this is very interesting regarding the reactivity of the material, especially if you want to have some application when we want to have suberin at the surface of the particle. So in this presentation, at this time, even if I speak a little about the chemistry of the lignocellulose powder, we didn't go too much into the mechanosynthesis. And in my last part of my speak today, I will present you an example where we can go further into the mechanochemistry. So this work was conducted in the farm work of the Elia Biomata. So I just introduced it at the starting of my presentation. And our aim in this study was to design, in fact, some bio-based material for doing bio-based sensor. In this study, we want to work with a matrix which is fully bio-based. So for that, we decide to work with some PLA, PHA, starch blends, so some materials which have a very low environmental impact, but also we try to work with some material which have very low footprint for the production process. So for this reason, we are very interesting about the PHA and the PLA and such materials. So we want to combine 3D printing and the bio-based materials, just to reduce the quantity of raw materials that we use, but also to design some technical shapes. So I really like to share this picture with plenty of funny objects. So in fact, these objects are not very useful, but it just demonstrates that we can obtain some very interesting shape. So what we saw in previous work, we saw, for example, for the milling of flax fiber, so I previously speak about that when we are milling this material, we have modification on the FTIR spectra of the materials. So most of the time, it's just oxidation phenomena. So we have some more alcohol and OH bond and CO bond, so just an oxidation. But we believe that, in fact, we can use that for grafting directly some molecule. So first of all, we previously did some tests or where we chemically graft a fluorescent probe onto the materials. And so we success to print some different objects that can react to pH as illustrated here. So in the study we conduct in the farm work here, we just try to see if we can chemically graft these materials and if there is a relation between the milling energy, I speak about that previously, and the efficiency of the grafting. And also we compare the result we obtain with the chemical grafting. So we decide to work with hemp core fiber. So why hemp core? Sorry, not hemp fiber, but hemp core. So why hemp core? So hemp core is a woody material. So it's a woody part of the hemp fiber. It has the cellulose and the hemicellulose composition present on the right of the slide here. And why these materials? Because it's a byproduct, so it's not useful for other application. And also we conduct previously tests, and we saw that we don't know currently why, but with this material, it seems to work quite well. So we decide to graft a mechanical reactant, a fluorescein, onto the material. So here you have the fluorescein and the different form that the fluorescein can take according to the pH. We work in a small ball mill, the small ball mill that I previously showed to you. So it's very interesting ball mill because in this one, now all the models that we have, we're able to calculate the impact energy and the total energy that we have. So we can totally manage the grafting process by the energy. So we work with the 2 grams of hemp core and the fluorescein 4 milligrams. And after that, the main question was to quantify the quantity of fluorescein that have been grafted onto the materials. So for that, we work with fluorescence, solid state NMR, FTIR, but today I only present the result obtained with fluorescence. So the first point was to do a calibration curve, as you can see here, and we were very happy because we obtained quite a good fit with a correlation coefficient of 0.98, so which is quite good for experimental result. And then we conduct an experimental design in which we increase the total milling energy and the impact energy. So our aim was to see if the grafting rate can be related to the impact energy or the total milling energy. So I just calculate in all cases the milling energy and the total milling energy. So maybe you can not see a lot the difference between the fluorescence rate, but just here without the calculation, we can see that we obtain the best grafting rate in the case where the total energy is higher, but it seems that there is no influence of the impact energy. So the impact energy is the energy of just one impact, and the total milling energy is the impact during the total duration of the milling. And we can see that there is a huge difference between the control, which have no fluorescence at all. So yes, in this case, mechanical grafting seems to work. So after that, we try to see if we can have a linear correlation between the quantity of synergy and the total milling energy and the quantity of graft fluorescein. And once again, it was very interesting because in this case, we obtain a very good correlation with a fit with a correlation coefficient of 0.98, and based on statistical analysis, we can see that all our results are significantly different. And we see no variation of the quantity of graft fluorescein with the energy of one impact. So it means that the total impact energy is the only very important point in this case. And the other points that with this method, we obtain the same grafting rate that with chemical grafting. So this was also a very interesting point. The main question where we are doing that, as we are working with, in fact, lignocellulosic material, so it's quite difficult to know which bonds are involved into the mechanochemistry that we are doing. The question is, could we speak about covalent bonding, or is just weak bonding? So for that, we conduct some fluorescence tests. And so we compare powder before milling, the control, mechanical graft, and chemically graft powder. For us, the main point interesting, so between before milling and control, we see that there is a difference in the intensity of peak. So this is probably related to oxidation phenomena that I previously spoke. And if we compare mechanical graft and chemical graft, it's very interesting because for mechanical graft, we see here a peak, the peak 3, which is less present here and not exactly for the same wavelength. The more interesting point is that the excitation long wave of the fluorescence is 490. And in the case of mechanical graft, we can see a shift on the excitation wavelengths. So this means that we have not the same environment in the case of mechanical graft in comparison to chemically graft. So for us, it's a very interesting point, but we need to go further and try to understand which type of bond is involved in this case. So just to conclude about our result, about the direction that we want to take now. So we can say that for the test that we conduct with mechanical graft powder, we have a very good reproducibility with 2 series. We have a strong correlation between milling energy and graft fluorescein. I didn't speak about this point, but we also look about the agglomeration in the graft powder, and for that we saw that a lower impact energy reduced the agglomeration, so we can also play on that with a quite good grafting rate. Next stage for us is now to understand which type of bond is involved in this case and how we can manage that just to create some functional particles for the future. So thank you so much, and if you have some question, I will be happy to answer.
Thank you very much for that presentation. I have a few questions. Let's start with this one. You showed that different materials, for example,
Sorry. I heard nothing. Are you here?
Yep. Did you hear me?
Yeah. Could you repeat, please?
Oh, I'm sorry. Did I cut out? I'll try again. So you mentioned differences in results for different materials, specifically bark and straw. And the question is, even within the same family of materials, could there be differences for plants that were grown under different conditions?
So I'm not sure to understand fully the questions. So it's 2 different types of materials. In fact, straw and bark, they come from different parts of the plant. And so for us, it's very interesting to, even if it's lignocellulosic materials, they have not the same ratio of cellulose, hemicellulose, lignin, and they are made of different tissue. And so the structure of the plant is totally different. And so as the structure is totally different, they will react totally differently in the milling device, in fact, because there is some defect into the materials, and the fracture path will propagate through this defect. And we can manage that just to try to obtain, for example, different shape or different surface composition.
All right, thank you. All right, this is one on a later part of your talk. Can you explain more why total milling energy is more important than impact energy?
So this is in the last part. In fact, the impact energy is just the energy of one impact. So it means that we can manage that by playing on the frequency of the ball mill. So in this case, so it's not necessarily the case for all, but in the case of mechanical grafting, what we think and what we saw at this stage is that we need to add plenty of energy just to graft the molecule. But between the different impact energies that we use, there is no difference. So it means that we are in the same rank of energy on which we can act on the chemical bond, even if there is some difference. The difference is not enough to see something different just for the bonding, just for cracking, in fact, the covalent bond. So in all cases, we crack the covalent bond, but what we need to crack plenty of bond just to graft enough material on it. But for example, for other factors like agglomeration, I didn't present the results, but in this case, if we have a very high impact energy, we are creating more agglomeration. Because in this case, the agglomeration is more a physical phenomenon than a chemical one. In this case, you are pushing the particles together, and so you create, I mean, not covalent bond, but you create some interparticular force that are stronger with an impact energy than in the case with a high impact energy than a lower impact energy.
Got it. Thank you. All right, here's a question. You mentioned that you're not able yet to isolate chemical bonds. Can you share with us some directions that you're going to, in the future, determine which bonds are breaking or forming and when?
So this is very interesting, and as in fact lignocellulosic materials are very complex, what I plan to use is to use artificial intelligence, and so to conduct different tests and just to work on that with artificial intelligence, just to go to something to more in-depth understanding. We can work on model. We start on working on cellulose, hemicellulose, and lignin. I mean, some more pure molecule. But the problem is that really believe, in fact, that the way that the particles are together into the plant materials is very important. And so if we separate the materials, we will not have the interaction between the lignin, cellulose, and hemicellulose. So I want to go in a more holistic approach. And for that, I think machine learning tools can help a lot.
All right, thanks. Let's do one more question, another broad one. So there's many exciting applications for these green technologies. What do you think is the most, the lowest hanging fruit or the most near-term potential application for these types of products?
So you mean for plant powders?
Anything that might come from products that would come from mechanochemistry-based research.
So this is a very difficult question, I think, because I'm pretty sure that we don't know yet all the potential application. So I can speak about some applications that we know today. So for example, in biocomposite field for materials, so I just think that combining mechanochemistry and, for example, 3D printing, as I present, allows the design of some sensors. So for application, it can be for food application. For example, I present some few things that reacting about pH. I also conduct some work. It was not fluorescent, but it was anthocyanin that we graft onto plant powder, similarly about what I present there. And in this case, the anthocyanin was coming from the red cabbage, so it can be something fully useful for example, food packaging. So, and we can have a change on the color on the food packaging. So this is a quite easy application. I also believe that not for all the biomass, because it depends on the type of biomass, but it can have some application, for example, in pharmacy, cosmetic, if there is no allergical problems with the powder, so it can make the powder more sustainable for tomorrow. Not from chemistry, traditional chemistry, but from a natural source of molecule. So I really believe that we can go in this direction. It's too early at this stage, but I'm pretty sure that if we unlock the understanding, we can go further in this direction. Also, there is other application for energy. because if we manage very well the particles, the energy content, the flowability of the particles, we can think about some example in energy. For example, in the past, I worked about using some powder directly into an engine to feed an engine, but for this we need to manage very well the composition, the surface composition, the flowability. So I believe that there is plenty of other applications that I don't know today, but if we go further in this direction, we will probably know them in the future.
Great. All right. Well, thank you again for your presentation.
Yeah, thank you.
Thank you so much, Dr. Mayer, for that excellent presentation. And thank you for joining us. Just a reminder that we've had a great group of speakers so far as part of the mechanochemistry discussions, and they're all available to watch anytime on the YouTube channel. We also encourage you to join us for the upcoming speakers in the months ahead. Thank you again for joining us.